Good afternoon, everyone. I'm before you today to present our final thesis presentation. First, let me welcome the esteemed members of the committee, friends, families, and industry members. While the individual cost of microprocessors is getting cheaper every day, the total cost of electronic components in modern vehicles has reached about 40% of the total cost. And in response to the increasing demand for technology in automotive systems, the number of ECUs, electronic control units, is getting higher, and so as the cost. That's why our team, made up of Ahmed, Omar, Andrew, Ali, Mohamed, and myself, under the supervision of Dr. Mohamed Shalan from the AUC and Dr. Ahmed Moro from Siemens, we decided to find a solution. But first, let us dig deep into the problem. The number of ECUs in modern vehicles has reached about 150 in high-end consumer products. And this number accounts for about 40% of the total cost and is projected to reach 50% by 2030. And this does not only affect the cost, this also affects performance. But first, you may ask, what's an ECU? ECUs are electronic control units. They're tiny computers that exist in each and every vehicle. And they're responsible for specific functionalities like powertrain, infotainment system, or brake system. Speaking about performance, this graph demonstrates a correlation between increasing number of nodes in a network system and the reduction of performance. And in automotive systems, the main network protocol is the CAN, and it is the first component that's being affected by this problem. In terms of security, increasing a number of nodes in a system increases the points of vulnerabilities as well. And that's why the market is shifting for a more sustainable solution. And that's by incorporating software hardware co-design and adopting multi-core architectures. However, while doing our research, we found a gap in the open source community, that we didn't find a project that is comprehensive enough to compete with proprietary solutions or even serve as a foundational element for a project that do so. And that is why today we're introducing Utopia OS, an open source, AUTOSAR compliant operating system that is tailored for multi-core architectures. And this is our roadmap. So first we'll discuss how we implemented our single core OS and the migration process to our multi-core architecture. And then we're going to discuss the ecosystem that we implemented, which is called Utopia. And then we'll finalize by the accelerators.
Okay. As we said, that we aim for implementing an operating system that is for automotive industry. So our first step for this operating system is implementing the single core AUTOSAR compliant OS. How to implement the single core compliant OS? We need to start with its building block, which is OSIC operating system. So we needed to build the OSIC operating system. So what is OSIC? OSIC is a standards that was founded by German companies in the automotive industry in 1993. And it is a German term that stands for open systems and corresponding interfaces for the automotive electronics. Okay, what is the purpose behind founding OSIC? The purpose behind founding OSIC was for cost reduction purposes, and this maintained by three ways. By maintaining the same OS architecture for all automotive systems, and as well as OS applications reusability and the best use of the OS resources. So we implemented the OSIC using on two steps. First, we implemented the hardware independent components, which are task manager, OS execution control, hook routines, event mechanism, and resource manager. All these components are the core components for the OSIC operating system. So as we can see that the OSIC operating system built we uses tasks, events, resources to communicate together in a real-time harmonic communication to maintain the best performance for the operating system. Next step was implementing the hardware-dependent components, which is OSIC, which are, I would like to start with our context switching implementation. For our context switching implementation, we utilized on the data structures of the tri-core, which are, and we used this to get the best performance that is dedicated for this microcontroller. Then for the user kernel separation, it maintained the separation of concerns. The traps manage the communication between the API to the user kernel, from user to kernel, and then the interrupts was implemented to maintain the predictability and decidability of the system, as well as the hardware alarms, which maintained the periodic scheduling in the system. As we said that OSIC was a building block for the AUTOSAR. Now, by implementing, we reach the next step, which is implementing the AUTOSAR. So AUTOSAR is a typical standards that is extended on OSIC standards that aim for the same purposes, but this time it was globally agreed on by the global companies in the automotive industries around the world for the intelligent mobility of the systems. And AUTOSAR stands for Automotive Open System Architecture. Now we know what is AUTOSAR. So first we implemented the feature of the stack monitoring in the AUTOSAR, which aims for detecting the stack overflows, and counters features which which acts as abstraction layer between the timers and alarms, and finally the OS applications that encapsulates the OS objects.
And now for our second achievement, which is a multi-core operating system. To support multi-core operating systems, AUTOSAR proposes several features and requirements. Among these, the main ones include the startup of the cores, cross-core communication, and cross-core processing. For the startup of the cores, AUTOSAR suggests a master-slave approach, in which the master core is always the first core that gets activated, and it can then activate other slave cores. And other slave cores that have been activated can also activate other slave cores, as shown in this diagram. For cross-core processing, AUTOSAR mandates that cores are able to start processes across other cores, such as activating tasks or setting events or setting alarms. To facilitate this, each core must be able to initiate a system call across other cores, as each system API in our operating system is mapped to a system call. Also, synchronization in this process is vital. Take, for example, if a core is trying to activate another task in another core, it must wait until that task is activated before continuing execution. Now, finally, for cross-core communication, AUTOSAR requires that cores are able to communicate with each other. To facilitate this, we implemented the inter-OS application communication layer, or in short, the IUC. The IUC, from its name, manages communication between OS applications. And since each core in our operating system has an instance of an OS application, the IUC thus manages communication between cores. The IUC provides APIs such as IUC send and IUC receive to facilitate communication between the cores. I'll now let my colleague Ahmed continue about the migration to multi-core.
Now, after our discussion for the single core OS and some of the supported features in the multi-core OS, we have to unpack and understand the multi-core migration process. The multi-core migration process can be divided into two phases, software migration and hardware migration. But let's have a quick reminder. We are dealing with an automotive operating system, time-sensitive and real-time operating system. So we have to set three different objectives while dealing with those. Separation of concerns, decidability, and predictability. How was this implemented? Through something called OS applications, which is an AUTOSAR requirement. Let's have a higher view of the OS applications. Each box of those acts as an encapsulating umbrella for different OS objects. And each of these in our shown assembly line will be assigned later to a certain core to preserve the separation of concerns. If we have a zoom in for the OS application, we can see that OS application contains different OS objects like the alarm, tasks, and ISRs. Now for the software migration, as we have decided the objectives, we had to deal with same code base and shared global common variables between different cores. So we had to implement two methodologies. The first one is the independent scheduling, and the second one is the locatable entities, which is the OS applications. For the hardware migration, we adopted a similar approach to have a certain key to be assigned to a certain hardware utility. For example, if you have a timer, you will assign it a core ID, and then it will be assigned to a certain core. Hence, we have implemented a pair core configuration for each of our hardware utilities. Now, I want to take you through a journey to map a real-life example of an automated emergency brake system and map it to a use case of our system to understand the backstage and what's happening in real life. At the beginning, we have the startup phase. We have two currently working cores. Let's imagine that we'll deploy a sensor system on core 0 and we'll deploy a brake system on core 1. In this core that contains the two cores, when the core gets a closer proximity to the another core 1, the sensor system will check and send using the AUC send API the data, and the core 1, which is the brake system, will receive the data, and then the car will stop or slows down effectively. What we can see from this example is that we have a working multi-core scheduling of the tasks and the cross-core processing between activating different tasks in different cores, and also the IOC, which was Mohamed was discussing for the communication between different OS applications.
Okay, so now let us talk about Utopia. Utopia is our AUTOSAR ecosystem. We have managed to create an ecosystem that is well-rounded and consists of components that complement each other. First and most importantly, the operating system itself, which is a multi-core AUTOSAR compliant operating system. The ecosystem also includes compliance tracking, which is consistent of both testing and traceability for the operating system, ensuring its correctness and its compliance with the AUTOSAR standard. Finally, we also have an OS generator that we have created tailored specifically for our operating system. Let us first start with testing. In general, the testing phase is a very important phase in any project. That's why we had rigorous testing for our operating system to ensure its correctness and its compliance with AUTOSAR. We utilized we started the system by starting the operating system and then running each test case one after the other while cleaning the operating system between each test case, as if it started from the beginning. We utilized flags like markers that indicate whether each test case has passed or failed. We have a total of 35 test cases that are divided as shown here and they help us in verifying that our implementation for the operating system is correct, and in verifying its compliance with the AUTOSAR standard. Now let's move on to the traceability. For automotive software development projects, adhering to the AUTOSAR standards is crucial. It sets a benchmark for the quality, scalability, and robustness of the project. So understanding how well we follow the AUTOSAR rules is essential. That is why our AUTOSAR traceability plays an important role in our ecosystem. It tells us how much we're meeting the AUTOSAR rules. So AUTOSAR gives us a list of requirements. It's like a checklist that we need to cover while building our operating system. An example is this table you can see here that gives us some of the requirements from the AUTOSAR document. To track how much we've finished from these requirements, we add inline comments, as you can see in the code above, that next to the implemented component from from the AUTOSAR document. Then we use a special program or a script that goes through our code and parses it and tells us how much we've met the requirement. After doing this, we found that for our single core operating system, we are 85%. We have 85% compliance with AUTOSAR Scalability Class 1. For the multi-core counterpart, we are 67% compliant with the AUTOSAR Scalability Class 1. Moving on to another very essential aspect of our operating system, of our ecosystem, and that is the open source nature of our ecosystem and of our project in general. Since we are the only open source multi-core AUTOSAR compliant operating system that we could find. However, since our target hardware is not available to the public and is actually protected by an NDA, we were not able to provide the implementation for the hardware-dependent components in our open source repo, but instead we provide a guideline for possible people to implement it.
Now moving to another important component in our ecosystem, which is the OS generator. The OS generator is a code generator that empowers the user to create tasks, resources, ISRs using a user-friendly AI. To be able to accomplish this, we used two main software tools. The first one is React.js. We used React to implement a user-friendly GUI to enable the user to interact with it and build the system attribute and pass the JSON data to the Python backend using Flask, and then the Python script will generate the required files and folder. And now we will demonstrate a live video that display what happened in the automotive field. Now the user are entering three different tasks called powertrain, APS, and Blinker in different cores, as the video demonstrate. Also add two different category interrupts called the can request and a parking sensor, and add a software counter. Also fill the associated alarm and fill the required alarm. Then add three different tasks and remove one of them to cater for human error and ensure reliability. The second video demonstrates after the user click generate button, the generator will create the IVT files corresponding to user action. Also, it will create the header files, source and header files that initialize the task and ISR previously mentioned. And the generator will initialize the tasks that user needed and keep the other unused task uninitialized, as the video demonstrates. Okay, moving to another important component in our project, which is code documentation. We used a software tool called Toxygen that is used for documenting C and C++ codes, which is our case. And we use it to develop our documentation page, which display a key features in our system, such as dependencies, file structure, how to contribute, and so on. Also, our documentation page demonstrates the class structure and its associated attribute using collaboration graph. In addition to that, also our documentation page enable visibility into header source files with dependency graphs, providing in-depth understanding of our system architecture and functionalities.
And now for our fourth achievement, which are the accelerators. Nowadays, microprocessors come out with accelerators to provide performance. As some applications have a bottleneck on the CPU, taking most of the CPU's time, we can use hardware accelerators to offload the CPU and thus provide performance. Our team chose to focus on the two accelerators which are provided by the TC49X microprocessor, taking in consideration both practicality and feasibility, and we chose to focus on the configurable digital signal processor and the cybersecurity satellite. For the CDSP, which offers functionality to perform digital signal processing operations, such as filtering, after further exploration, we had to put this accelerator to the side due to missing documentation. As for the CSS, which provides functionality to perform encryption, decryption messages between the cores, we implemented the APIs to support this module, and they are ready to be tested.
Now, to conclude our presentation, we will leave you with a promotional video for our system, showing the key features of our system. So, let's go.
In the heart of innovation, meet the Tricore TC4X microcontroller, the building block of our revolutionary operating system. Our implemented ecosystem thrives, showcasing the adaptability of our operating system across devices and various applications. Empowering developers, RO's generator simplifies the complex, making customization and adaptation a seamless process. Built on the principles of collaboration, our operating system is an open source project fostering innovation and inclusivity. Lastly, our detailed documentation serves as a guide, ensuring smooth integration and a wealth of resources for developers. From components to the heart of your ride, our operating system powers the driving experience, ensuring safety and efficiency. Zooming out further, witness the impact as our operating system transforms individual vehicles into a connected network, shaping the smart cities of tomorrow. From microcontrollers to a connected world, our Autopia ecosystem drives the future of technology. Join us on this transformative journey.
Great. So, hello. Okay. So we would like to also extend our thanks to Bashmans Ahmed Ansari and Bashmans Hesham from Siemens, Bashmans Ahmed Abdelghani from the AUC.